Let's get started. I want to introduce our next speaker. He's a senior architect for Mellanox, focusing on software solutions, Richard Graham.
So what I'm going to talk about today is some of the work that we've been involved in over the last several years in terms of trying to improve the characteristics of InfiniBand from scalability and performance perspective. And so specifically, I'm going to talk about a new transport, dynamically connected transport. For those of you that were here last year, I gave a brief overview of this. The Verbs level support for this is about ready to be GA'd here very soon, or to be released, publicly released. And so part of what I'll talk about is the new Verbs API, the extensions to the Verbs API to support these capabilities. So really, what we're trying to address here from a technical perspective are several issues. First of all, provide a scalable communication protocol that supports high performance communication protocols, that's asynchronous and that's reliable. So the intent here is to part of the intent here is to remove software from the path as much as possible and let hardware that can usually do things much more efficiently be the main driver here in the communication protocol. So prior to dynamically connected transport, or DC, there are two transports, two InfiniBand transports that are primarily in use. The reliably connected transport and unreliable datagram. And so the RC, or reliable connected transport, supports RDMA, atomic operations, and is a very high performance transport mode. One of the main issues when it comes to large scale is that if you need to communicate with a large number of destinations, your resource footprint required for these tends to grow quadratically if you look at the system as a whole, and therefore is not very scalable. You could build around these things like some sort of connection caches, but these tend to be expensive. I mean, you have to set up, tear down connections and the like, so somewhat expensive. On the other hand, you have UD that's very scalable. You have one queue pair, and you can use that queue pair to communicate with any other UD queue pair in your system. However, it doesn't support RDMA or atomic operations. And if you care about reliability, and there are applications that don't care about reliability, but if you do care about reliability, you have to handle that in software. And so you have the software overhead of managing reliability. And so what DC, or dynamically connected transport, is really intended to address is the issue of providing a scalable high performance protocol. And what DC is a reliable protocol. So it supports RDMA and atomic operations, but it's also scalable in the sense that you can use one queue pair to communicate with any other DC endpoint in the system, and so you get the scalability that you want. See, I forget what I have on the slides here. Okay, so from a resource perspective, here's a historical view of the amount of the number of queue pairs that are used that have been used with the various transport modes. And as I mentioned before, reliably connected transport, the number of queue pairs scales basically as the number of processes squared. So you can get improvement by going to XRC. That improves things some, but still you have that n squared dependency, where n now, instead of the number of processes, the number of endpoints is the number of endpoints divided by some small number. So you get better resource utilization, but still you have the fundamental problem of having an n squared type of scalability, or if you look at the requirements of the memory requirements, for example, imposed on a single Q pair, it's still related linearly to the size of the system. RD no one uses, or not many people use, and so won't worry about that there. And so things get even a little worse when you start looking about issues around quality of service, multipathing, because the amount of resources that you use there also grows with the number of the type of resources you want to use. The other issue about XRC as well as RD, those all focus around resource sharing, and so there's contention at the endpoints for resource, and so the DC model really deals with these sort of issues. So the first thing about the DC model is it's dynamic in nature. That is, the connectivity is dynamic and it changes based on usage model, based on actual usage model by the application. There's no prediction or anything here. It really follows a particular application usage model on an application by application basis. I'm sorry. So from a model perspective, DC is an asymmetric communication mode. You have initiators and you have targets. So the initiator initiates traffic, and the target is as its name implies, is a target of data. And initiators are not targets. These are two distinct objects. In terms of resource requirements, on the initiator side, the application controls the number of initiators, and so and the number of initiators, it really depends on the nature of communication, and I'll get into that a bit more in a few minutes. Targets, there's a single target. That you only need a single target at the destination. You don't need multiple targets like you do with an initiator. And there's no resource sharing between communications between different pairs. From a resource footprint, this really so basically what happens when communications are initiated, all the application has to do is continue and use the send function that they use today, with the characteristics defining it as using the DC transport. And so the application, once a Q pair is open, just starts posting sends to that using that initiator to a given target. Initiator doesn't have to. The user doesn't have to do any sort of connection setup. The initiator doesn't need to know what target to address, but there's no connection setup. Once a user requests the communication to happen, at the hardware level, you actually do end up allocating resources for that pair, and the duration of those resources are really as long as it takes to satisfy the reliability protocol. And as soon as all traffic to a given destination has been delivered reliably, the hardware basically disconnects that connection. It's and so the very special, what this takes advantage of is an observation that a given node can only generate traffic there's an upper limit to the amount of traffic a given node can handle, whether it's sending or receiving. And regardless of how many posts an MPI might put, or how much data anything might try to send, the hardware and both CPU and HCA are not able to drive beyond a certain limit. And what that means is, in terms of initiator traffic, all one really has to have is sufficient initiator resources to hide the cost of the reliability protocol, which is fixed, independent of the size of the system. And actually, for our devices, it's not a large number of Q pairs. And so what that means from a resource perspective, regardless of the size of the system, you are capped in terms of the amount of resources that you need to use to support communication at full network capability. And that cap is fairly small in terms of resource footprint. The other point here, communication is set up by at the hardware level. There's no need for three-way handshake or anything like that, the way there is, for example, in RC today. It's very much akin to somewhat akin to UD, not exactly. So a cartoon here in terms of the amount of resources that are used by a library, for example, to support communication. Again, a historical perspective, giving here some resource utilization as a function of the size of the system. And we see that, at the time that RC first came out, the systems weren't large. And so this sort of memory footprint was okay. But over time, of course, the systems are growing, and new capabilities have been brought in to try and address some of the scalability issues. So we see with adding the shared receive queues, the resource footprint goes down a bit more. XRC helped here, but they still have this characteristic of increasing with increasing system size. With DC, the footprint is essentially fixed. And at a small value. So, as I mentioned before, here's a cartoon a bit about the some of the objects associated with DC. So you have the initiator. So I have here two initiators. They can be on the same source. They can be on different. They can be in the same process. They can be in different processes. Really doesn't matter. And they send data to different targets. You can have, as you see, there's a given DC can send a given initiator can send data to multiple targets, and a given target can receive data from multiple initiators. And it handles communication from multiple sources simultaneously. So you're not serializing here at the targets because you have a single target for a destination. So I should say there's nothing that prevents you from, if something like an MPI or so somehow wants to create more than one DC target, there's nothing prevents them from doing that. If somehow they want to segregate traffic, that's perfectly fine. So with RC, this is a cartoon, so you can have very dense connections. So you have an all-to-all type connection basis. When you go to Dynamically Connected Transport, the connections are really determined by the communication pattern of the application. As requests for communication come, communications are set up, and when a communication is done, they're torn down. Everything happens at the hardware level without the cost of some sort of round-trip latency or something like that. It really very fast. And so it really adapts to the usage by the application. So from a Verbs perspective, as I said, this feature is scheduled to be released at production level very soon here. And so we have a set of Verbs extensions defined for the DC transport. There are two types of objects. As I said, there's the DC initiator, which is really only a new QP type. So you have now UD, RC, RD, what am I forgetting, and DC. There's a target, a DC target, which is a brand new object. It's not a Q pair. It's a brand new object because what it actually does is it represents a lot of resources underneath the covers that handle a lot of connections. So it really is not a QP in terms of object behavior. A DC has associated with it a shared receive queue, a completion queue, and an access key that's very similar to the Q key that's used for UD. And of course, there's support to query the device to figure out if this feature is supported or not, and things to query about properties of the feature. So in terms of the initiator verbs, we use the extension to create QP, to create a new QP type. Here's the macro for it. And so in terms of QP creation, there's a new parameter that's used there to define the fact that we're trying to create an initiator. As I said, at the application level, the application, if they care about latency, and of course most applications do, you want to open more than a single initiator. Probably it really depends on the application profile. You don't need more than a few hundred at most on today's systems. In terms of the target verbs, as I said, this is a new object, and so there are new experimental verbs added to manage this object. There's an object that creates a target, an object that's used to destroy the target, and an object that's used to query the characteristics of the target. In terms of using the dynamically connected transport QP in send operations, the send verb has been extended to include the properties needed, the data needed to send a message using the DC transport. So as I said, there's a access key that needs to be sent with every message, and at the destination there's actually a check to make sure that the access key matches the access key of the queue pair being sent to. There's a DCT number that's basically a QP number, as well as an address handle. On the receive side, no API changes at all. Completion notification comes from the completion queue that's associated with the target, and that's really it. So that's, in terms of description of the feature and the new verbs, that's really all I have. Yes.
So do you need any new hardware component to support your PC?
So DC is supported starting with Connect IB. Yes, you do need. It's and the support is in the Connect IB card. Yes. Yes.
So if you're doing an API, how can you tell if you need to allocate maybe more of these initiator components? You have to tell from the hey, with the API, you might be better. They have one just a few, said maybe up to 100.
Said maybe up to 300 if you're trying to drive it as hard as you can. 300 total. So the question is, how would you know the number of initiators you actually need to use? So I can tell you what we did on what the initial design did. So the initial design basically had a pool of initiators, the MPI level design, I should say. And basically and one of the things we try to do is stick with the same initiator as much as we can. One, we don't want two initiators to be going in parallel to the same destination. The way we implement MPI, because it relies on network ordering, and so if you have, there's no ordering guarantees between targets. So what we try to do is maintain a single active initiator. And then if you get to the stage where you're having to reuse those initiators, that is, move them from one initiator to the other frequently, and you can measure actually the time to do that, then you know that you're in a position where you need to allocate more. Now this is I mean, we're still gaining experience here in exactly how to use it at the MPI level, to be honest. But this is an approach to the problem. So basically, if you're not thrashing, there's no need to change. Yeah, I mean, you can do pencil and paper, but pencil and paper doesn't help you in terms of actual user profiles, usage profiles, I should say.
So there's a wire protocol change required here as well. Did I understand that right from the key?
That's right. That's right. So the DC access key is 64 bits versus the Q key that's 32 bits.
Is there any negotiation of this capability from end to end?
No, no negotiation. It's a system-wide assumed to be a system-wide characteristic.
So where memory requirements is not a concern, in the sense for small clusters like 30 nodes, and assuming that there is enough memory, which will be more performant, DC or the other way?
DC or RC, you mean? Or
RC.
yeah. So RC doesn't have the overhead of establishing a connection. The overhead isn't large, but it's still overhead. I mean, the overhead is actually very small. So in the ping pong latencies, you don't see a big difference. In 0-byte MPI levels, ping pong latencies, you don't see a big difference. But if you have something static, is always better than something dynamic. I mean, if you have the resources. But this is really to deal with the cases where you don't want a very, very large resource footprint. And so when you get to, when you start getting to, probably order 100 or more end nodes, this becomes much, much more important. And actually, even before that, you can see performance differences. Did you?
Yeah, I was going to ask if you measured the kind of the delta in the message latency.
We have. We're not quite, since it's not GA yet. We're not. It's not final, so I won't comment on it. It's small, is what I'll say. It really is small, but it's not at final stage, so I won't comment on it. It's a fraction of the latency of the RC latency, a very small fraction of the RC latency. Let me put this.
How does this interact with the automatic path migration and reliability features? Is it transparent?
Yeah. It's an orthogonal feature.
After you've gone GA on Connect IB, any chance of seeing it on Connect X3?
No, it's a hardware feature, and ConnectX-3 does not have that hardware capability.
How does the initiator know about the TCP equipment number?
So that's something that has to be exchanged, just like you have to exchange any other key information, or whether it's memory key, whether it's Q key. I'm sorry?
The RCQ-based destination QP number is similar to that.
That's right.
It changes in every course. So it still needs to be negotiated out of band.
There's no negotiation. When a process sets up its target, it assigns it an access key. That access key has to be exchanged. There's no negotiation. That access key has to be exchanged up front, and then it can be used. It's set up once for every target.
How does the connections are drawn down?
The hardware handles that. The hardware has a mechanism for both setting up and tearing down the connections.
So what was the argument against doing RD?
So RD allows you only one outstanding message at a time, and so it's not very useful from a performance perspective.
So if you were to extend that, like what's preventing like a specification of RD that does multiple outstanding?
If you were to extend that, I'd have to look at the RD spec to see. I think I can guess on a few things. I mean, the basic issue is you have to have a way to hold reliability context, and you have to agree on some sort of mechanism for doing that. And so you could, if there's nothing that prevents you from taking, RD, and basically gutting it and put something else underneath it, calling it RD or something like that. But
Yeah, so like can I call this RD? Right?
no, you can't call it RD because RD means something very specific. But it has the same sort of notion. No, it doesn't, because it's not datagram. It's actual messages. Yeah.
Are there new knobs for sysadmins like control the behavior of this? Because it sounds like there might be things like timeouts, and not in a bad way, but like how long the hardware.
No, that's right.
Hold on to one of these temporary connections.
Yes.
Not tear it down, so you can control that.
So temporary connections, no. Temporary connections, if the hardware has nothing to service, it will tear it down. So in Connect IB, no. For other things, yes. There are definitely configuration parameters that are set for controlling aspects of managing these queue pairs. So when timeouts and things like that. Okay. Thank you.